All right, so today we're starting the next topic, which is complex numbers. So complex numbers, as it suggests, are complex. So complex in that they have two components. So they have a real component and an imaginary component, and we'll get onto that. So the question, of course, is if it's got an imaginary component, then what is an imaginary number? So this comes back to the 18th century. As it says there, the imaginary number was introduced, and there was a few different mathematicians that had a hand in this imaginary number. And so the key thing is this one right here, that I squared is -1. All right, so if you think by definition, I squared is -1, so I would be the imaginary. So what that then allows us to do is we can now find the square root of a negative. Ooh, a negative number. All right, is now possible. All right, so up until this point, what we've been working is in the real number field, and of course you can't square root a negative number in the real number field, but in the complex number field you can. And it's using this I squared equals -1. So an example might be, say if we have the square root of -9, for example. Of course, -9 is the same as 9 times -1, and -1, of course, is I squared, so it's 9 times I squared. So the square root of 9 is 3, and we'll go plus or minus 3, and the square root of I squared, of course, is I. So we have square roots of negative numbers that are possible, and using the I, so replacing the negative by I squared, and then square root of I squared, of course, is just I. All right, so that's the imaginary component. So what is a complex number? All right, so here we go. We got a couple of. So we normally use complex numbers Z, A plus B I. So this I part, you can see there, it's got two parts. It's got just the normal A, and then it's got the B, which has got the I attached. And A and B are real numbers. So this A is the real component, written like that, R-E-Z, and the B is the imaginary component, so written as MZ. All right, so that's basically, that's it. That's a complex number. So Z equals 2 plus 3i. That is a complex number. It's got a real part, 2, and an imaginary part, which is 3. And we know it's the imaginary part because it's got the I there. All right, so if we look now, expanding a Venn diagram, drawing a Venn diagram of numbers, it's like these concentric circles. So the complex number field is this outside, and then within that we have real numbers. All right, and within that we then have rational numbers. Within that we have integers, positive or negative, and then within that we have our natural numbers. All right, so the numbers that we already know don't exist. This just adds an extra ring, if you like. So the real numbers are a subset of the complex, is what it says there. If I haven't Oh, excuse me. So if I had a number like this, for example, whoops, z equals 3 plus 0i, that would normally just be z equals 3. And so z equals 3 is just a normal real number. So whenever b is equal to 0, what we have is, oops, run that wording together, we have a real number. All right. Okay, so let's have a look at some examples. So if, let's have a look at 4 equals 3i, 4 minus 3i equals 2a plus bi, find the values of a and b. Okay, so what we're going to do is look at the real part. So looking at the real part, so equating the real part. So real and imaginary parts. So the real parts, 4 equals 2a. So if we divide both sides by 2a would be 2. And then b is this bit, equating the imaginary part. And so over here on the left we've got -3 equals to b. And so there's no more rearrangements that we need to do there. All right, next. Same sort of idea here. Find the values of a and b where these two numbers are equal. So again, you're looking at equating the real parts and the imaginary parts, and then solving. So what do we know? We know from the real part, 2a plus 3b is -1. And from the imaginary part, so that's the real part, from the imaginary part, we have a minus 2b equals 3. All right, so we need to solve these. So I've got 2a there and just 1 there. So what I'm going to do is times all that by 2. And so when I do that, I get 2a minus 4b equals 6. I'm just going to bring that one down to a plus 3b equals -1. I've got to eliminate the a's, so if I subtract, I now got 2a minus 2a, which is no a's, minus 4b minus another 3 is -7. 6 minus a minus a plus 7, so b is -1. So if b is -1, I'm going to put that in here. A minus 2 times -1 equals 3. A plus 2 equals 3. A equals 1. So there's our values of a and b. All right, so that's a little bit of an introduction. Now, what can we do with complex numbers? Well, we should be able to do the same things with complex numbers as we do with all numbers. Add them, subtract them, multiply them, divide them, etc. Graph them, all those kind of things. So let's start with addition and subtraction. So the process is that we work with the real and the imaginary parts. All right, so really, I've gone straight into it. Gone straight into a question here rather than. So if we've got, say, z1 plus z2, then what we would do is add our real parts together and add our imaginary parts together. And if we've got z1 minus z2, then we would subtract A minus C, subtract our real part of Z, subtract our imaginary part of Z2, I should be saying. So B minus D I. Alright, so here's an example. So for part A, Z1 plus Z2. So we've got the real parts, 2 and minus 4, and the imaginary parts, -3 and 5, and we're adding them together. That's minus, so it's -2, -3 plus 5 is 2, plus 2i. Alright, then if we were subtracting Z1 minus Z2, then we've got to subtract the real part of Z2 from the real part of ZA, and we've got to subtract the real part of the imaginary part, not real, the imaginary part of Z2 from the imaginary part of Z1. All right, it's a plus there, so it's 6, -3 minus 8, I. And there we are. All right, next one is if we're just multiplying by just a whole number. So 5 times Z1. Oops, that's not A, it's C. So C, 5 times Z1 is simply 5 times, what is it, 2 minus 3i. And then we expand that bracket the same as we would always expand brackets. 5 2's are 10, minus 15i. Alright, so that's it, multiplying by whole numbers. So far, it's fairly straightforward. Alright, there are some things that for imaginary numbers, there's some, because of that I squared equaling -1, there's some interesting things that happen when we do powers of I. As it says here, there is a pattern which repeats after 4 terms. So let's have a look. So I to the 0, so anything to the 0 is 1, no change. I to the 1, well, it's just an I, no change. I squared, well, the definition of that's -1.
All you need now is a little PA up over here to screen the people knocking on the door, mate.
All right, little interruption. All right, so I cubed then, well, as we know, it's I squared times I. And I squared is -1, so that's going to be negative I there. Now, the next one, I to the 4, is, if I split that up, I'm going to split it up as I squared times I squared, which is -1 times -1, which is 1. And then I to the 5 is I to the 4 times I, and I to the 4 we just found out is 1, so that's just I. So you can see, looks like we're now starting to repeat that pattern. So I to the, oops, not T, I to the 6 is I to the 4 times I squared. I to the 4 is 1 times -1, which of course is -1. And then the next one, I to the 7 is I to the 6 times I. You can break these up in, which is -1 times I, which is -I. All right, so you can break those up using the index laws however you like. They're just what I've done. So as you can see here, there's a pattern here that goes 1, I, -I, -1, -I, and then goes around in the circle again. All right, so we can use that kind of thing to help us. So here's some examples. Simplify I to the 13, and then this other one will go I to the 13 first of all. So I to the 13. So we've got to think about, using the index law, how can we split up I to the 13? Well, if we go I to the 12 times I, then the I to the 12, well, we know from here that I to the 4 is 1, and 4 3s are 12, I to the 4 times to the power of 3, again using one of those index laws in reverse. And so I to the 4 is 1, so that's 1 cubed times I, so I to the 13 is just the same as I. This one here, we've got some stuff we need to do before we get into this. So what I need to do is I need to cube all of that. So I've got 3I to the 4 times -2 cubed I cubed. So we've got 3 there. You can remember that's times, and so is that, times -2 to the 3. Better put it in brackets so that it's, I'll remember that it's -2 times -2 times -2, not the negative of 2 times 2 times 2. So that's -8, and that's I to the 4 times I cubed. Now, what we know then is that I to the 4, so from what we did over here, I to the 4 is 1, and I cubed is I squared times I. All right, so I could have scrolled back up, but I didn't. So 3 times -8 times 1 times -1 times I. We've got 3 times -8 is -24 times 1 is -24 times -1 is 24. So it looks like we've now got 24I as our final answer. All right, so there we go in terms of those things. I think that's about it for the moment. For the moment. We'll do multiplication and division next time. There's a little bit more involved. We can still do them, all right? But the processes of those things that we've looked at today are pretty close to what we do with our real numbers, and we certainly think the processes that we use, the index laws, the expanding the bracket up here, when we add bits together, subtract bits, all of those things, they're all the same processes that we're using. All right, so first exercise, some practice of that stuff, and as always, have fun.